Uranium, that heavy gray metal buried deep within the Earth, is one of the most dangerous and simultaneously influential materials humanity has ever extracted. Capable of shifting the global balance of power, it is the core component of both nuclear energy and atomic weaponry, and its existence has altered the entire course of history. Yet, a question rarely asked is, how does this subterranean stone transform into energy that lights up entire cities? How has man managed to extract tens of thousands of tons of it annually, only to convert it within facilities protected by the world's most stringent security systems into fuel that powers nuclear reactors with a capacity that gives even superpowers pause? So how exactly does this journey unfold? And how is it transformed into a lethal weapon that terrifies the world? This is what we will explore in this video. But before we dive in, if you're new to the channel, make sure to hit the like button and subscribe. First, we must understand what we are talking about. What exactly is uranium? Uranium is a heavy, naturally radioactive metal with a silvery gray color. Found in the earth within rock ores such as uraninite, the world's largest deposits are located in Canada, Kazakhstan, and Australia. But what distinguishes uranium from all other metals is its atomic structure. In nature, uranium primarily exists in two isotopes: uranium-238, which makes up 99.3% of the material, and uranium-235, which accounts for only 0.7%. This tiny percentage is the key to everything, as uranium-235 is the only isotope capable of triggering nuclear fission, the process in which a heavy atom splits into two smaller atoms, releasing a massive amount of energy. The figure that is mentally difficult to grasp is this. Imagine that just 1 gram of enriched uranium releases energy equivalent to more than 3 tons of crude oil. 3 tons from a single gram. This is the reason for the intense interest in this metal, and simultaneously, the reason for the danger it represents. However, uranium-235 at its natural concentration of 0.7% is not enough to power a nuclear reactor. This concentration must first be raised to between 3% and 5% through a process known as enrichment. But before reaching the enrichment stage, there is a long journey that begins deep underground. The most profound point in uranium's journey isn't the nuclear reactor, but rather the very beginning, mines reaching depths of up to 450 meters below the Earth's surface. Among the most famous and largest of these mines are those located in the northern part of Saskatchewan, Canada region, considered one of the richest in the world for high-grade uranium reserves. The challenge with these mines is that they do not resemble any ordinary mine. The uranium ore layer lies beneath a sandstone rock formation saturated with groundwater where pressure is constantly high. Any drilling error could mean the potential collapse of the mine and its flooding. To avoid this, engineers developed a highly precise drilling technique using drill bits made of tungsten carbide, one of the hardest known alloys, to pierce the earth and create hundreds of small holes in the area surrounding the ore body. These holes are not only used to reach the uranium, but also to insert steel pipes through which calcium chloride is pumped at a temperature of 30 degrees Celsius below zero. This substance completely freezes the soil and groundwater around the ore body, forming a solid, protective ice wall that prevents any collapse or unexpected leakage. Once the ground is stabilized, the actual drilling phase begins. Massive expansion drills, equipped with high-speed rotating blades and pressurized water jets, are lowered to cool the drilling area and push rock fragments upward to the surface. All these operations are conducted remotely without the direct presence of workers in the area, as the radiation at this depth poses a significant health risk. The raw rock fragments containing uranium are pulled through specialized suction pipes or dropped into underground storage chambers, then transported via vehicles with thick lead lining. Every day, a single mine can extract and send between 500 to 1,000 tons of ore to the processing plant. Upon arrival, a multi-stage chemical journey awaits the ore, gradually transforming it from coarse rock masses into a material suitable for enrichment. Stage 1. grinding, and crushing tins. Ore are poured onto a conveyor belt that leads first to a primary crusher with massive steel gears, breaking down large rock chunks into pieces no larger than a few centimeters. Afterward, these pieces enter a large ball mill containing thousands of solid iron balls that rotate at high speeds, constantly colliding with the rocks until they are converted into a fine powder resembling coarse sand. Stage 2. Conversion into slurry. The powder is mixed with water in large industrial stirring tanks to turn into a thick paste known as slurry, which is easy to transport and process. This paste passes through a spiral classification system where screw blades rotate to push the material upward, while the heavier granules settle at the bottom that are removed. Stage 3. Chemical extraction. This is where the true separation begins. The slurry is transferred to massive reaction tanks where specialized chemical reagents, such as sulfuric acid, manganese dioxide, and iron salts, are added in precisely calculated amounts. These substances react with the impurities in the ore and convert them into stable, insoluble forms. Thus, unwanted minerals are removed while the uranium remains dissolved in the solution. Stage 4. Evaporation and yellowcake production. Uranium-rich solution is transferred to large distillation tanks where the material is heated to over 800 C for up to 24 hours. The water gradually evaporates, leaving behind a dense substance with a distinctive yellow color that gives the material an appearance similar to turmeric. This product is what is known in the nuclear industry as yellowcake, and it contains up to 80% pure uranium. Yellowcake cannot be enriched directly. It must first be converted into another chemical compound known as uranium hexafluoride. This is achieved by dissolving the yellowcake in potent hydrofluoric acid and then gradually heating it inside a stainless steel reactor until it transforms into a gaseous state. This gas is extremely hazardous because it reacts violently even with trace amounts of water, producing toxic gases. Consequently, it is stored in tightly sealed steel cylinders and handled with extreme caution at every stage. It is then pumped into centrifuges, a system of thousands of interconnected devices that rotate at speeds exceeding 50,000 revolutions per minute. Here, the laws of physics work in the engineer's favor. Since uranium-235 is lighter, it tends to concentrate round the central axis of the rotating chamber, while uranium-238 moves toward the walls. This system is monitored by hundreds of sensors that track vibration, temperature, and pressure, as a single failure in one device could affect the entire array. The final product is enriched uranium with a concentration ranging between 3% and 5%, which is sufficient for use as fuel in civilian nuclear reactors. This uranium is packed into specialized steel drums equipped with leak detection sensors and marked externally with radiation warning signs and precise tracking codes. Enrichment is not the final stop. The enriched uranium is subsequently converted into uranium dioxide, a fine gray powder. This powder is placed into specialized presses that exert immense pressure to shape it into small cylindrical pellets, no larger than a medical capsule. Accuracy here is a necessity, not a luxury, as any variation in the weight or density of a pellet could directly impact the performance of the nuclear reaction within the reactor. These pellets then undergo a process called sintering, where they are heated in a specialized furnace to approximately 1,600 C. This intense heat causes the uranium dioxide molecules to fuse tightly, creating a stronger, more stable structure capable of withstanding the massive pressures inside the reactor. Once hardened, the pellets are placed inside metal tubes made of zirconium, a unique metal that withstands extreme heat and does not absorb neutrons during the nuclear reaction. When the tubes are filled, both ends are sealed using automated laser welding. These tubes are known as fuel rods, and dozens of them are bundled into a lattice framework called a fuel assembly. This assembly is the fundamental building block that powers nuclear reactors around the world. To give you an idea of its capacity, just one fuel assembly is capable of generating enough electricity to supply approximately 10,000 homes for an entire year. That is an immense amount of energy. The fuel assemblies are placed into the core of the nuclear reactor, where the fission process begins. Neutrons collide with uranium-235 atoms, which then split into smaller atoms while releasing massive heat and additional neutrons that continue to strike other atoms. Maintaining a steady and controlled chain reaction, the generated heat is transferred through a heat exchange system to boil water and produce high-pressure steam, which drives massive turbines connected to electrical generators. A single reactor is capable of producing enough electricity to power an entire modern city. Can you imagine this staggering power? After about a year of operation, the fuel assemblies have exhausted most of their energy and are then replaced, but they are not simply thrown away. These spent assemblies remain hot and radioactive, so they are submerged in deep cooling pools within the plant, where they cool down gradually and are safely isolated. Transitioning from fuel to weapon, the essential differential through the journey begins in the same mine. The path diverges completely at the enrichment stage. While a civilian reactor requires uranium enriched to only 5%, an atomic bomb requires highly enriched uranium with the concentration exceeding 90%. At this extreme level, the reaction transforms into an explosion that releases energy equivalent to thousands of tons of TNT. The same centrifuges we observed are capable of creating a weapon. They simply need to continue spinning for longer periods to raise the concentration to levels of mass destruction, and so, the journey of uranium is complete from a rock buried deep within the earth. Through highly complex mining stages, precise chemical processing, and enrichment in centrifuges spinning at tens of thousands of revolutions per minute, reaching the fuel pellets placed in the heart of a reactor that lights up entire cities or destroys them with an atomic bomb. This journey is one of the most complex technological achievements ever realized by humanity. Now, I have a question for you. If the discoverers of uranium had known from the very first moment that it would be used to create a weapon threatening human extinction, would they have stopped their research? Or would the allure of infinite energy have overwhelmed them? Let me know your thoughts in the comments. We have now reached the end of the video. Thank you for watching.